So this is the third part of the video, and in this video I will show you the applications of Euler's formula. Why do we have to learn Euler's formula? All those application, and I will tell you those application in this part of video. Okay, so applications of Euler's formula. Okay, now one of the important application about this Euler's formula is the following Euler's theorem. Now this Euler's theorem tells you a very important equation, or you can say relation between numbers relative prime to each other and the congruence relation. So if you have two integers a and n, okay, for example a and n, they're both positive, and if the GCD of a and n is equal to 1, that means they're relative prime, then a to the power e of n, okay, is in fact equal to 1 modulo n. Okay, so in other words, we can always find a power which makes a equal to 1 modulo n. And remember before, when we are talking about congruence relation, okay, usually we have a very huge number, and usually we have a number in the form like a power, okay, and it's huge, it's very big, and it's impossible for us to use calculator to compute the value explicitly. Okay, that's impossible. Okay, but using congruence, we can sort of reduce the value, because usually we only consider the remainder. Okay, when you're dividing that number by some other positive integers, we want to find the remainder. Okay, and how do we get the remainder? Again, you take the congruence. Okay, you take the congruence, you keep reducing the value until you get the number which is between 1 and the divisor. Okay, then you get the remainder. Not 1, I mean it should be 0 to that number. Okay, because the remainder can be 0 anyway. Now how can we do that? Usually one key step, okay, is to get this, okay, get some power which make the integer after you take the power, that will be equal to 1 after the congruence. But it's not easy to get that, because you have to, if you have tried those problems, you have seen those examples, we have to observe the pattern. Okay, now sometimes if you're lucky, then you can observe the pattern easily, but if you're not lucky, then maybe you have tried several times in order to see, okay, how many powers should I take in order to get 1 after you take the congruence, right? Now this Euler's theorem tells you that you don't have to be very lucky, but you just have to be hardworking. I mean, if you remember this Euler's theorem, then you can apply this theorem to get a power which makes your number equal to 1 after the congruence. Okay, and that power is nothing but just the Euler formula. Okay, so let me show you one example. Okay, so rather than just keep saying this abstract formula, so for example, find the unit digit of 7 to the power 222. Okay, again, this this number is so huge. Okay, if you want to compute it directly, it's impossible. Okay, so the solution is the following. So we need to find the number r, or I should say positive integer r, such that, okay, 7 to the power 222 is equal to r after you take the congruence relation, congruence to 10 modulo 10. Okay, because this is something we did in the last video. If you want to find a unit digit, then you just have to solve that congruence relation modulo 10. Okay, and you have to make sure this r this r has to be less than or equal to, I mean, r is bigger than or equal to 0, but it's less than or equal to 9, okay? Because if it's 10, then you can just take another congruence, you get 0. Okay, so that's why you won't hit 10, but you can always make sure the remainder is between 0 and 9. Okay, so that's your goal. Okay, once you get this number out, you get the unit digit. Now, since GCD of 7 and 10 is equal to 1, okay, it's quite obvious because 7 is a prime number. Okay, so if 7 is a prime number, there's only two choices, only 1 and 7 to be the GCD. Now it's clearly 10 is not divisible by 7, so GCD must be equal to 1. So GCD of 7 and 10 equal to 1. So by Euler's formula, I should say Euler's theorem, okay, the theorem we just proved, okay, then we can we can do what? We can take the power 7 to the power e of 10. That always give me 1 modulo 10. Okay, now as I said, that is a very useful information because it reduces the number. Okay, because after some power, you know that 7 to that power give me 1. So that can significantly reduce the value. I mean, reduce the value of 7 to the power 2 to 2. 7 to the power 2 to 2 is too big, right? Now your remaining task is to, of course, evaluate that e to the power 10 and see the relation between this number and 2 to 2. Okay, that's not the end because you have to find the unit digit of this original number. Okay, now e to the power 10, what is it? This is equal to e2 times e5. But you know that this is just you can use the formula whatever you like it, e minus 2 and 5 minus 1, and that exactly give you 4. Okay, so we know 7 to the power 4 equal to 1 modulo 10. Well, if you have a good memory, okay, so in fact in my previous videos we have seen that relation already. 7 to the power 4 always give me 1 modulo 10. Okay, but now we use another formula to get the same answer. Okay, now using this we can reduce the value for 7 to the power 2 to 2. Very easy because now you can change the power into this. Okay, 55 times 4, because 55 times 4 is 2 to 2. No, sorry, 50 is 2 to 0. Okay, so you still have another part which is, okay, so let me just write in that form, 7 to the power 2. Okay, because 2 to 2 you can change. Okay, so let me just put one more line there. Okay, 2 to 0 plus 2. Okay, and then you use the index law. Okay, you split the index. If you have a sum on the index, you can split it into a product like this. Okay, so and in particular 2 to 0 is just 55 times 4. Okay, now this part 7 to the power 55 times 4, this number is equal to 1 because if you don't see that, okay, I can write one more line and you can see the relation. This is this number and then times 7 to the 7 to the power 2. Okay, this is again we just play around with the index, and it is 1. Okay, so after you take the congruence, that is 1, and if you raise it to any power, it's still equal to 1. So that part give you only 1. Okay, so it's not important. So the second part is more important. So the second part is 49, right? So 49, so 1 times 49, that is modulo 10. But you know, after you take the congruence, 49 is nothing but just 9. Okay, modulo 10. So therefore, the unit digit of the original number 7 to the power 222, that is just equal to 9. Okay, so you see, this is a very useful application about the Euler's formula, or you can say Euler function, whatever, because this is a way for us to get a number which make the power equal to 1 after you take the congruence. Okay, so there's a special case, in fact, as a special case for Euler's formula, Euler's theorem. Okay, is this. Okay, if P is a prime number, then and if P is a prime number and GCD of A and P, okay, is equal to 1, then you have this relation A to the power P minus 1, that is always equal to 1 modulo P. Okay, it's exactly a special case for the Euler's theorem, because now the proof is very easy. Okay, for example, if you want to prove it, so now using the Euler's, okay, let me look down a little bit, Euler's theorem. Okay, we already have this A to the power E of P equal to 1 modulo P, but we know that E of P, that is equal to P minus 1. Well, this is something we did already at the very beginning, the fact EP equal to P minus 1. So because of that, so we have A to the power P minus 1 is equal to 1 modulo P, which is exactly what we need. Okay, so it's a very special case of Euler's theorem. Okay, if you have a prime number, and if it happens that you have to take the congruence with respect to that prime number, then you have a very good chance to get some power, which after you take the power, that will give you the congruence 1, except that you have to check whether this number A is relatively prime to P or not. Well, in this case, that means if A is not a multiple of P, then of course they must be relatively prime, because P is a prime number. Okay, so as long as A is not a multiple of P, then you always have GCD of AP equal to 1. And then you can use this special case to get this relation. And actually this is called the Fermat's theorem. Okay, so even though it's a special case, in fact there's a name for this theorem. Okay, it's called Fermat's theorem. And in fact, I think I have this in my notes as well, so you can also check it from the notes. So in fact, it's exactly the same, but I just pick it and then want to explain it here. Okay, so this is the application about the Euler's formula, or you can say Euler's function. Okay, and the most important application I would say is about the congruence relation. Okay, because it tells us some powers, okay, which make the huge number, like, I don't know, 7 or whatever, 7 to the power 222, just like the example, make it smaller and smaller. Okay, reduce the value, because we can use this congruence relation to change some number to be 1. Okay, this is the crucial part in solving that kind of problem, because the original problem is too big. Okay, there's no way for you to know the exact value. So in order to know the exact value, in order to solve the problem, you have to apply those formula and then reduce the value. Okay, after you take the congruence, you can reduce the value. Okay, the congruence relation is like you can keep chopping multiple of some numbers. Okay, and by chopping it, you will reduce the value. Okay, once you reduce the value into some numbers which you know how to do the computation, then you win the game. you can get the unit digit or whatever you want, okay, the remainder. Okay, so that is the application about Euler's formula. And now I think you guys will know a lot about the congruence relation. Okay, and I hope you all guys know how to solve the problems regarding congruence relation. Especially if you have a very huge number, you should be able to reduce it into some smaller numbers and then get the congruence relation correct. Okay, so that's the end for this video. Okay, and if you have any question, again, you can send me emails or anything. Okay, just to let me know if you have any question or you have any difficulty in understanding the material. And by the way, the notes, they should be available on Moodle. Okay, so I will also upload the notes, okay, as well as this Word file. Okay, I will maybe make some changes, correct some typos, and then I will upload it on Moodle as well. And then when you're watching this video, you can have the notes and have this not the PowerPoint, but this Word file, and see if you can get the reference. Okay, so that's the end for this video.